Today we are here to talk about the definition of function, the verification of function, and the inverse of it. We'll be discussing about the definition of function first. To start off, what actually is a function? A function is a unique relation. An association from f a to b is said to be a function if each and every element of domain has unique association with elements of codomain. Here we have the two postulates for a function. First of all, we have participation. From participation, we mean that each and every element of the domain set should take part in association. And from uniqueness, we mean that each and every element should be associated, but it should be uniquely associated. Now, we're going to take the example of the relation fx equals x plus 3, and we're going to discuss how it is a function through the postulates that we have discussed before. Here we have the elements of the finite domain, and likewise we have the elements of the finite codomain over here. Now I'm going to replace the elements of domain with respective elements according to the example right here to prove that this relation is a function. Now I'm going to replace this element with 1, this element with 2, and finally this element with 3. Likewise, 1 will be associated with 4, 2 will be associated with 5, and 3 finally will be associated with 6. Now, I would like to put forth a question. Is this a function? If we look at the postulates, first of all, we have participation. Now, is each and every element in the domain set participating in an association? We find the answer to be yes. For example, 1 is in association, 2 is in association, and 3 is in association. Second is uniqueness. Is each and every element in the domain associated with a unique element in the codomain? We find the answer to be yes again, because 1 is only mapped to a single element. This is same for all the elements present in the domain set. Now, what would happen if I would take this element and add it to the domain? Will this still be a function? The answer is no. First of all, each and every element is not participating in an association. So, the first postulate seems to be violated. In conclusion, we are not going to call this a function. But what if I put this over here? Is this still a function? There is nothing wrong right here. Each and every element of the domain set is associated. And each and every element is associated with a unique element in the codomain. Therefore, even if this element is left unassociated, it does not violate the postulate. We call this one-to-one function, but a better name for this would be one-to-one into. Here we have the function f equals x squared, a finite domain, and a finite codomain. Here we are going to verify from this if the relation here is a function. First of all, if you look at the participation of each and every element, we can see that every element is participating in an association. Now, for uniqueness, is each and every element in the domain set mapped to a unique element? We find the answer to be yes. -1 has only one image in the codomain, and this is similar for all the elements in our finite domain. As you can see, the previous elements from -1 to 3 over here. Now, the same question. If I put 7 in the domain set, will this still be a function? In this case, it will not be a function because 7 is not taking part in any association. So, the first postulate is being violated here. But, what if I put this element and take it into the codomain set? Will this still be a function? As we discussed earlier, this will still be a function, but it will have a more distinct name, which will be many-to-one into. Now, let's move on to the inverse functions. Starting off with the definition, when a function f a to b is bijective, there exists a function f inverse b to a called the inverse of f. A question for everyone watching. Are all functions invertible? The answer is no. Only bijective functions are invertible. Now, what does the term bijective mean? Bijective means that a function is both one-to-one and onto, something that we discussed earlier. Now we are going to discuss about the invertible nature of quadratic functions and linear functions. Taking the example of the linear function y equals x plus 3, we are going to explore the invertible nature of it in the algebraic way. This is the conventional method which involves changing the roles of x and y to obtain the inverse. When you change the roles, we obtain the inverse as y equals x minus 3. If you look at 1, 4, 2, 5 and 3, 6, these are the points on the locus of the original function, and 4, 1, 5, 2, 6, 3 are the points on the locus of its inverse. If we look closer, we can find that 1, 4 is being changed to 4, 1. This means that the x and y coordinates are being interchanged. Now going into the geometrical interpretation, the green line is the locus of the original function, whereas the red line is the locus of its inverse. If you look closely, you can see that the green line is being reflected from the line y equals x. So this is the reflection of it. Generally, any geometrical structure reflected from y equals x is the inverse of it. Let's move on to the inversible nature of quadratic functions and start off with an example of y equals x squared. Going to the algebraic process, here we are going to reverse the roles of x and y as done previously and find the inverse to be x equals y squared. Analyzing this in the ordered paired way, these are the points on the locus of the original function. Likewise, these are the points on the locus of its inverse. Looking closer, we can find that the x and y coordinates of the yellow balls are being interchanged. Likewise, the coordinates of the red balls are being interchanged. Furthermore, if you look at this geometrical structure and then look at this one, we can find that these two are being reflected from the line y equals x as mentioned earlier. Generally, any geometrical structure that is reflected from y equals x is going to be its inverse. But that question can be answered by plotting a line. This is called a vertical line test. A vertical line test involves drawing a vertical line. If there is more than one intersection, then the geometrical structure is not considered a function. If you try to answer the question of why this was not a function, we should look at the definition of functions, which tells us function is only invertible if it is bijective, and y equals x squared is not bijective. Another way to put it is that y equals x squared is not one-to-one and onto.